The last problem in this section is a story problem that we're going to try and find a minimum area. So we're going to take our concepts we learned about rational functions and we're going to apply it to a minimum area problem. So a rectangular page is designed to contain 48 square inches of print. The margins on each side of the page are 1.5 inches wide. The margins at the top and bottom are both 1 inch deep. What should the dimensions be of the page so that the minimum amount of paper is used? Draw an equation for the rational function, or determine the equation for the rational function algebraically, then solve numerically and graphically. So what we've got here is we've got a page that's going to have 48 square inches of print, and then we've got some additional margins. So I'm just going to draw a general picture for now. I'm just going to make this rectangle shape. And this is going to represent the page that I'm working with. Now, I know that I'm going to have 48 square inches of print and there's margins on each side. So inside here, I'm going to draw another box. And this box is going to represent my 48 square inches of print. And we say the margins on each side are 1.5 inches wide. So 1.5 here and 1.5 here. And then 1 inch up and down. So first thing we want to do is just draw this picture. The second thing is that we know the area of the print has to be 48 square inches. But I have no idea if it's a 6 by 8, a 12 by 4, a 24 by 2. That's the area inside of here. I don't know if this is 6 by 8 or 12 by 2. So what we're going to do for now is we're going to represent this as being just an x and y distance. So x and y. And we know that the x times y distance is going to be an area of 48 square inches. So we've got our picture, and now we want to figure out just how all these different things are related. So let's just write out our dimensions. We know that the x dimension of the paper is going to be the entire length right here. This x represents the x dimension of the print, but what's the x dimension of the entire paper? And that's going to be x plus 3. So that's the length from side to side of the paper. The second thing we want is the y dimension of the paper, which is going to be y plus 2. So my end goal of this problem is to figure out what is the area piece for the length and the width, this x and y value. What I then can do then is once I know it's like a 6 by 8, a 12 by 2, I can then plug the x and y values into these two equations to figure out what the dimensions of the actual paper are going to be. So let's start out with what we know. We know two facts about area. One is the printed area, and then one is going to be the minimum area. And our area the formula for an area is always length times width. Or in this case, it's going to be x times y. So we want to find this area, and this A is going to be the minimized area of the paper. So this big A that we're talking about is going to be the area of the entire page. So how do we find the area of the entire page, this entire thing? Well, it's going to be the length times the width. And if we know the x dimension of the paper is x plus 3 and the y dimension of the paper is y plus 2, my area is going to be x plus 3 times y plus 2. Now the issue that we have there is we sort of have 3 variables and one equation. Can't really do much with that. So let's use another equation. The other piece that we know is this inside area is 48 square inches of print. So let's write the area of that. We know 48 is equal to x times y. Now that I've got this equation, let's simplify the second equation and then we can substitute into the first equation. Once we simplify and then substitute, we then will have a rational function in terms of area. It'll be area equals everything here. And the way I'm going to choose to do this is I'm going to solve the second equation for y. So y is equal to 48 over x. And the reason why I choose that is as soon as I solve for y, I can plug this 48 over x in place of y in this equation, and then everything is in terms of x, which is what your calculator handles. So we solve in terms of y in this case, and then we'll plug into original. So area is equal to x plus 3, and then 48 over x plus 2. Now everything is in terms of x's, and we want to just simplify this a little bit. So then I can just write out my rational function. So here, x plus 3, 48 over x plus 2. If I were to find a common denominator in here, I would have 48 over x plus 2x over x. So I'm just going to write that as a single denominator. And then when I multiply those two pieces together, it's the same thing as the whole thing being over x. So there's the first part, determine the equation for the rational function algebraically. So there's the area that is going to be minimized for this area of paper. So that's the function that we're going to use. The next thing we need to do is we need to figure out the minimum. So we found out algebraically what the rational function is going to be, and now we're going to solve numerically and graphically what that minimum is going to be. So we're going to pull out our calculator for this. So turn on your calculator, and into y1 we're going to plug this in. And I already plugged this in ahead of time. X plus 3, 48 plus 2x all over x. And we hit graph. And when we look at that, that really doesn't give us a lot of information. We can see this graph crosses the x-axis, it looks like at -3. But negatives aren't going to help us in terms of determining dimensions of paper. If I plug in negative values here, I'm going to end up with negative dimensions of paper, and we don't want that. We want our dimensions to be positive. So we want everything to be larger than a -3. If I plug in -2, -2 plus 3 would give me a positive 1, and maybe the x dimension would be 1 to minimize. But let's see what we come up with. I'm going to go to the numerical view temporarily. And if I go back to my starting point, which is 0, and I start looking on my table, I can see the total comes down for this area. Remember, these x's indicate inputs, these y's indicate output, and for this function here, the input indicates the x value for the inside here. Actually, I take that back. The x is actually it is that x right there. And the area indicates the y output. So here, if we look at the x, that's going to give me my x dimension. So if I put in a 1, I'm going to get an area of 200. That's not what we want. If I plug in a 2, I'm going to get an area of 130. If I plug in a 3 for the x dimension, I'm going to get an area of 108. I want to find the minimum y value. So I'm just going to scroll down here. And I can see that somewhere in here, I hit 88. There's 88.5, 88, 88 again, and then 88.4. So my question then, is there something in between here that makes my values less than 88? So I'm interested in what happens really between 7 and 10. So I'm going to go to my table set. I'm going to start at 7, and I'm going to go 0.25 instead of 1. And let's see what happens. Well, I can see here at 8 was 88, which I knew. And then 8.25 is 87.9. 8.5 is 87.941. I can see right here I'm getting a little less, and then I come back to my 88. So at 8.5 there, I'm at 87.941. So probably ask myself, well, can I go any smaller than that? Well, if I then go to start at 8 and let's go by 0.1, do I get any smaller? And I can see if I go by 0.1s, I sort of, at 8.5 right there, I'm still at 87.941. So my guess is somewhere around 8.4, 8.5, somewhere in there, I'm going to have a minimum value. So there numerically is my analysis. I don't have the exact answer, but I can at least numerically determine what that's going to be. Now, why I chose to do that is I'm going to make a little note here that I like something that 8.4 is going to 87.943, and 8.5 is going to 87.941, and 8.6 is going to 87.944. So somewhere between that 8.4 and 8.6 is going to be my final answer for this. But if I look at my graph, all I see is that. So for this graph, I need to change my window a little bit so I can see what are these values that I'm working with. So I'm going to go to my window, and I'm going to go from 0, and we know we're looking at 8.4, 8.5, so we'll go 20 with an x scale of 2. Gives me a little bit more than I need. And then for the y minimum, I'm looking at somewhere in the 87. So let's go 0 to 100 with an x scale of 10. And then we'll hit graph. And I can see right there, somewhere right around here is going to be the minimum. And how we calculate the minimum, we can go to second, calculate, and choose minimum. And we know we're going to be between 8.4 and 8.5. So 8.2, 8.7 sounds good. And there's my minimum. My minimum's at 8.485, and then the y value being 87.941. So I'm going to do a little graphical approach here, that if I were to draw this picture out, the minimum is going to occur at 8.485 and 87.941. Now that really doesn't give us the whole picture yet. We want to know what the x and the y values are. So this right here is our x value. What is the y value? And we can find the y by going back to one of our original equations, which this one's probably the easiest to work with. Y is equal to 48 over x. So y is equal to 48 over that 8.485. So we get y is equal to 5.657. Now, does that actually tell me what the length and the width are going to be? No, it really doesn't. What this tells me is that the y height here is going to be 5.657, and the x length here is going to be 8.485. So that tells me the printed area. So it's not an 8 by 6 or 12 by 2 that we thought. It's this decimal combination of 8.485 and 5.657. My final thing is I want to find the dimensions of the paper, which is x plus 3 and y plus 2. So the dimensions of the paper, if I say x plus 3, that's going to give me 8.485 plus 3, which is 11.485. And then y plus 2 is equal to 5.657 plus 2, which is 7.657. So 11.485 and 7.657 are going to be the dimensions that produce the minimum amount of paper used, given the fact that I've got to have 48 square inches of print and margins of 1.5 inches on each side and 1 inch at the top.